Hey people, today we're going to do a couple of videos, a couple of problems from our OpenStax book. So let's get started. Half-lives. We're going to talk about exponential growth and decay of common terms associated with exponential growth and decay. Okay, half-lives. The formula for radioactive decay is where T is in time and years and H is the half-life of the substance. A of T is the amount of time the substance at T time. And A naught is always, like we discussed in class, is always the initial amount of the substance. So this is our formula that we would use right here. A of T equals to A naught times 1/2 to the T divided by H. Okay, the carbon life. So let's do an example. The carbon life 14 has 730 years. A fossil is found that has 12% carbon 14 found in a living sample. How old is the fossil? So we would use one of these formulas right here to figure out how old some of these fossils would be. So we don't have a lot of information besides we have the carbon life that has a life of 5,730 years, and then we also only have that it is 12%. Okay, so let's just start by using our formula. A of T equals to A naught of 1/2 to the T divided by H. Okay, so since there is a remaining of 12%, that is half of the life of the 5730 years, which is a fraction of the percent, perhaps we can divide our A naught by both sides, right? And we will be left with A of T over A naught equals to 1/2 to the T over H. And the reason why I put that is because we're in this place, right, where we have 12% of this amount that is remaining, right? So that means this would be 0.12 equals to 1/2 we are trying to figure out how much time, but our carbon half-life is 5,730 years. Now we have to just simply solve. As I discussed before, you have to know how to solve for exponentials. So we would take the natural log of both sides, and I'm just going to write this as a natural log of 0.5 instead of using a half each time, to the T over 5730. Now, we're still solving for T, so that's the reason why we took the natural log. Now we have to use that power rule. Remember the power rule? If we have log base B of m of n, remember the exponent comes down to the front, even for logs and for natural logs. So this exponent T to the 5730 is going to come down to our front. So this should be the natural log of 0.12 equals to T over 5730 times the natural log of 0.5. Okay? Now we need to solve for T, right? So we are still going to divide both sides by the natural log of 0.5 from both sides. Okay, this will cancel. And now we are left with, didn't give myself enough space. We are left with the natural log of 0.12 divided by the natural log of 0.5 equals to T over 5730. Well, the only way to get rid of the 5730 from the denominator is to multiply both sides by 5730. So when I multiply both sides from 5730 on the right-hand side, it goes away. And t now equals to the natural log of 0.12 divided by 50, natural log of 0.5 times 5730. Now we have to put this into our calculators to make sure we have it all together. So we have 57, well here, let me clear it all out so you're not confused from something. 5730 parentheses times the natural log of 0.12 close the parentheses divided by the natural log of 0.5 close parentheses, and we end up with our time being 17,527.46. So 17,500, I lost my number, 27.46. And let's remember, what did it tell us by what year? And we're going to round our answer to the nearest year. So this 46 cannot bump that up. So equivalently, this would be 17,527 years. And that would be our answer. Now, if we move on to the logistic growth model, we use this in some instances when we are doing logistics for our business people. The logistic growth model is approximately an exponential at first, but is reduced at a rate of the growth of as the output approaches the model's upward bound. The carrying capacity, okay, and it's called the carrying capacity, I'm sorry. For constants A, B, C, the logistic growth of a population over time x is represented by the model f of x equals to c divided by 1 plus a to the e to the negative bx, where c divided by 1 plus a is the initial value. C is also considered to be the carrying capacity, and B is the growth rate. Okay? So if we want to find this out, f of 0, right? Our first question. If we find f of 0, 130 divided by 1 plus 6e to the negative 2 times 0. We're plugging in 0 for our function. Well, when we plug this in, this will give me 130 divided by 1 plus 6e to the 0. Anything to the 0 power is going to give me 1. So this will be 130 over 7. Okay? 130 over 7, if I plug it into my calculator, is going to give me 130 over 7 is going to give me 1857. 18.57 is my answer. Now, the question asks us, what does this interpret? F of 0 interprets our initial amount, okay? Miss Parker can't spell. I could spell. Initial amount, okay? Now, the next question we have, all right, for our second question, the population P of a fish farm in T years is modeled by the equation 2600 divided by 1 plus 9e to the negative 0.7t. Okay, our first question asks us, what is the initial population? So again, in order for us to find the initial population, remember, initial population is C divided by 1 plus A, right? So we would just simply do 2,600 divided by 1 plus 9 equals to 2,600 divided by, excuse me, 10. So these zeros will drop off, and 260 would be my initial population. Okay. The next question says, to the nearest whole number, what will the fish population be in 2 years? So if you recall, T is always going to be time, right? So we are simply just plugging in T for 2. So 2,600 divided by 1 plus 9 e to the negative 0.7 times 2, which will give me 2,600 divided by 1 plus 9. I have to just plug it in the calculator. Actually, so this will be 2,600, okay, divided by parentheses 1 plus 9 e, okay, to the negative 0.7 times 2, close parentheses twice. And then I end up with 807, and it says round to the nearest whole number. So again, 807.6. So this 6 can bump up the 7. So that would be 808 would be the fish population. All right, I should try to have another video up on word problems on the boiling point. Thank you.